Hello everyone. Today we are going to discuss the chi-square test. It is also known as Pearson's chi-square test or simply chi-square. It is one of the most useful statistics for testing hypotheses when the variables are nominal, as often happens in clinical research. The chi-square statistic is a non-parametric tool designed to analyze group of differences when the dependent variable is measured at a nominal level. Like all non-parametric statistics, the chi-square is robust with respect to the distribution of data. Specifically, it does not require equality of variances among the study groups or homoscedasticity in data. What is homoscedasticity? If you must ask, then I can say that if we have collected certain amount of data and all the values in the data are having same kind of variance, then we can say that the data is homoscedastic in nature. Now, unlike many other non-parametric and some parametric statistics, the calculation needed to compute the chi-square provide considerable information about how each of the groups are performing in the study. Unlike most of the statistics, the chi-square can provide information not only on the significance of any observed differences, but also provides detailed information on exactly which categories account for differences that are found. Thus, the amount and detail of information this statistic can provide renders it one of the most useful tools in the researcher's array of available analysis tools. Like every other parametric or non-parametric test, it is having certain assumptions and conditions. Now we are going to discuss conditions first. So, it should follow certain conditions like the level of measurement of all the variables is nominal or ordinal, and the sample sizes of the study groups should be unequal for chi-square, as the groups may be of equal size or unequal size, whereas some parametric tests require groups to be of equal or approximately equal size. Here we are not having any compulsion to have a group size having equal number. Now, as I mentioned, we usually use nominal data, but under certain conditions we can also use an interval or ratio level data, but it should violate certain assumptions of a parametric test. Like, if we collect the data, it should be collapsed into certain categories, or I can say class intervals, where I can merge the data and make it into certain category. The data that we have collected should also violate the assumptions of equal variance, and the data should be seriously skewed or chaotic. Now we are going to discuss the assumptions of the test. Like, the data must be in frequencies or counts of cases rather than in percentages or some other transformation of the data. The next assumption would be the level or categories of the variables are mutually exclusive. That is, a particular subject fits into one and only one level of each of the variables. Each subject may contribute data to one and only one in the cell of chi-square test. If, for example, the same subjects are tested over time such that the comparison of the same subjects can be fit into different time slot, then we would say that we cannot use chi-square test. And the last assumption would be the study group must be independent. This means that a different test must be used if the two groups are related. For example, a different test must be used if the researcher's data consist of paired samples, such as studies in which a patient is paired with his or her child. Now, we are going to discuss the types of chi-square. The most commonly used type of chi-square test are chi-square goodness of fit test and chi-square test of independence. Both the test involves the variable that divides our data into categories. Now we are going to compare and contrast both of these types of square tests. In chi-square goodness of fit test, the number of variables should be 1 in number, whereas for chi-square test of independence, the number of variables should be 2 in number. The main purpose of chi-square goodness of fit test is to decide if one variable is likely to come from a given distribution or not. Whereas for chi-square test of independence, we decide if the two variables might be related with each other or not. For example, if I were given a bag of candy and I have to see if the number of pieces that are contained in that bag are having same type of flavor or not, then I'll use chi-square goodness of fit test. Whereas in chi-square test of independence, I could use a certain type of situation, like if I'm a owner of a movie theater and I have to see whether the people coming in my theater are dishing for snacks at certain movies, that I can find out the relation between the type of snacks and the type of movie people are watching. I can use chi-square test of independence here. Now, like every other test, we have to form our hypothesis. Here in chi-square goodness of fit test, we can say for our example that the proportion of flavors of candies are exactly the same. Or the alternate hypothesis can be the proportion of flavors are not the same. Similarly, for our movie theater like situation, we can form alternate and null hypothesis. Null hypothesis would be the proportion of people who buy snacks is independent of movie type. The alternate hypothesis can be the proportion of people who buy snacks is different for different types of movies. Now, here in every chi-square test, we find the degrees of freedom, which varies according to the test. Like for chi-square goodness of fit test, we find out degree of freedom by number of categories minus 1. In our example, the number of flavors of candy minus 1. So, and in chi-square test of independence, we find out degrees of freedom by number of categories for first variable minus 1 multiplied by number of categories for second variable minus 1. In our example, the number of movie categories minus 1 multiplied by 1 would be 1. So now we'll discuss on how to perform the chi-square test. For both the chi-square goodness of fit test and chi-square test of independence, we have to perform simple steps. Like we have to define our hypothesis like right before or right after collecting the data. And then we have to decide the alpha values. This involves deciding the risk you are willing to take of drawing the wrong conclusion. For example, if I set my alpha value at 0.05 when testing for independence, that we have decided that there is 5% risk of chances of failing my assumption. Now we will check the data for errors and then we will check assumption for test. And then we'll perform the test and draw our conclusion. Now comes how can we use chi-square in statistics. We can use in various forms, like we can determine the confidence level for a population standard deviation of a normal distribution from a sample standard deviation. We can also find out the relationships between categorical variables using contingency table. We can also find out independence of two criteria classification of qualitative variables. We can find out the sample variance study when the underlying distribution is normal. We can use the chi-square test as a goodness of fit test in general. Now, the chi-square statistic is one way to show a relationship between two categorical variables. In statistics, there are two types of variables, numerical variables and non-numerical variables. Numerical variables are countable and non-numerical variables are categorical in nature. The chi-square statistic is a single number test that tells you how much differences exist between your observed counts and the counts you would expect if there were no relationship at all in the population. Here you can see the chi-c square equals to summation of OI minus EI to the power square upon EI. Here the subscript C refers to the degree of freedom, O is our observed value and E is our expected value. There are few variations on the chi-square statistics. Which one we use depends on the type of data we are collecting and what hypothesis we are testing. As you can see, now we have modified our previous formula into the new one. Here you can see the upper limit and the lower limit for the data that we are computing here. Here O is the observed value, E is the expected value, I is the ith position in the contingency table. A low value for chi-square means there is a high correlation between the two sets of data. In theory, if our observed and expected values are equal, then chi-square would be 0, which is unlikely to happen in real life. There is no way that two data can be rendered equal. Deciding whether a chi-square test statistic is large enough to indicate a statistically significant difference isn't as easy as it seems. It would be nice if we would say that a chi-square statistic greater than 10 means a difference, but unfortunately that isn't the case either. So now we are going to discuss the p-values. A chi-square test will give us a p-value. That p-value tells us if our test results are significant or not. In order to perform a chi-square test and get the p-value, we need like two pieces of information mainly. The degrees of freedom, which is the number of categories minus 1, and the alpha value. The alpha value is decided by us or any researcher. The usual alpha value is 0.05%, but we could use any other values as decided by the table that we are given. The degrees of freedom are placed as a subscript after the chi-square symbol. This is the table that are usually given to everyone to calculate the p-value. Now, let's discuss chi-square distribution. It is a special case of gamma distribution. A chi-square distribution with n degrees of freedom is equal to gamma distribution with a equals to n by 2 and b equals to 0.5 or beta equals to 2. Let's say we have a random sample taken from a normal distribution. The chi-square distribution is the distribution of the sum of these random samples squared. As you can see in this graph, the degrees of freedom are equal to the number of samples being summed. For example, if I have taken 10 samples from the normal distribution, then df would be 10. The degrees of freedom in a chi-square distribution is also its mean. In this example, the mean of this particular distribution will be 10. The chi-square distribution are always right skewed. However, the greater degree of freedom, the more chi-square distribution looks like a normal distribution. Now, we'll understand the chi-square test by taking an example. Here, 256 visual artists were surveyed to find out their zodiac sign, and the results were these values. Now we are going to find out the chi-square value. Now we are going to follow certain steps. Like, first of all, we'll make a table with columns for category, observed, expected value, residual value, which would be observed minus expected value, the square of residual value, and then square of residual value divided by expected value, which would be our component. Now we are going to fill our categories with various sun signs. And now we are going to write the counts. These counts are the number of each items in the category in the column 2. Then we'll calculate the expected value. How we are going to calculate the expected value? Since there were 256 people and there were 12 sun signs, then we are going to divide both of them to find out how much people should be there for each sun sign. That would be our expected value. Now 256 divided by 12 would be 21.333. In the next step, we are going to subtract the observed value from expected value to find out the residual values. Don't worry if you see the negative sign, it is nothing to be feared of. And then in the next step, we are going to square our values and place the amount in the component section where we are going to divide it with expected values. And now you can see these values have emerged. Now, in the last step, what we are going to do is we are going to sum up all the values in the last column and we will get the chi-square statistic as 5.094. We have seen applications of chi-square test in business development and in medicine. Now we are going to discuss its application in other fields. We can use chi-square test in cryptanalysis where it is used to compare the distribution of plain text and possibly decrypted ciphertext. The lowest value of the test means that the decryption was successful with high probability. This method can be generalized for solving modern cryptographic problems. It can also be used in bioinformatics where it is used to compare the distribution of certain properties of genes like genomic content, mutation rate, interaction network, clustering to see how it affects certain categories like disease genes, essential genes, genes on a certain chromosome, etc. And these are the references where you can refer further. Thank you and have a nice day.